Thank you for joining us for another Breakfast by the Bay. My name is Jen. Behind the camera is Captain Eric, and you may be seeing a surprise appearance by him later on. But today we're here to talk all about buoyancy and density. Could you please do me a favor and give us some likes or let us know in the comments that you can hear us and see us okay? And we'll get started in just a minute. I'm just gonna give everyone some time to log in and catch up with us. If you're viewing from a school today, or if you're obviously at home, but could you please let us know what school you are from? We'd like to give you a big shout out today for joining us.
Okay, Captain Jen, I think we've got a few folks tuned in. It looks like Matthew just joined us, and Janine.
Welcome, Janine.
All right, let's get started.
All right, awesome. So we're going to be discussing buoyancy and density today, if you have just joined us. We want to know, why do things float and why do some things sink, right? Think about a large ship that's carrying cargo across the world, across the oceans. They usually have thousands of tons of cargo on their boats, and they're able to float. And how is that? So we're going to walk you through this today and explain how things float. But before we get started, we do have some really important vocabulary that you do need to know in order to understand and follow along. So first we're going to start off with mass down here. Now, mass is the measure of the amount of matter in an object, and that's typically measured in grams or kilograms. Now, how is mass different than weight? Well, think about your mass on the Earth and on the Moon. They would be the same. Now let's think about your weight on Earth versus your weight on the Moon. Where would you be heavier? You would be heavier on the Earth, right? And that's because of gravity. So mass and weight are different, but your mass is going to be constant, where your weight might vary depending on gravity. Now, mass is also independent of size. So imagine you have a soccer ball and a bowling ball. Which one is going to be heavier? Your bowling ball is going to be heavier, right? But your bowling ball will have greater mass than a soccer ball, even though they are the same size. Great, we're going to move on to volume here. Volume is the amount of space a substance or object occupies. And that's usually measured in things like liters or gallons or ounces, and there are quite a few more. Now, we need to know mass and volume in order to determine density. So density is going to be our third vocabulary word for today. Density describes how compact or concentrated something is. So, for example, if you have two boxes, one is large and one is small, let's say they both weigh the same. That would tell us that the smaller box is more dense, okay? And things will float or sink depending on their density. And so, to calculate density, you have to know mass and volume. So, we're going to be finding the mass using our scales, but we're also going to be using our graduated cylinders to find volume.
All right. So we know that volume can be measured by figuring out what an object's length, its width, and its height are. And if we measure all of those things together, we come up with their volume, which is measured in cubic centimeters or cubic inches. Today we're actually going to be using the metric system. So we're going to be using cubic centimeters for our volume. Now, that works pretty well for a thing like a box. I can even fairly easily figure out the volume of an object like this little plug of wood. But it gets a little harder when I get something like this.
Captain Eric, why are we using the metric system?
So the metric system we're going to use today because we've got a pretty interesting cheat in the metric system. The metric system is made so that 1 milliliter of volume is equal to 1 cubic centimeter, which is also going to equal 1 gram of water. So all of those things kind of tie together in a much nicer, easier way, and it makes it so that we don't have to do as much math. So that's why the metric system tends to work a little bit better for science, and it's why a lot of places, matter of fact, most places around the world use the metric system. So if I want to determine what the volume of these irregularly shaped objects are, I'm going to have a really hard time. Luckily, a really smart Greek mathematician by the name of Archimedes figured out how to do this a long time ago. The story goes that Archimedes was taking a bath one day, and he noticed that when he got into the bathtub, the water in the bathtub started to go up a little bit. I bet you figured that out too. So he realized that the amount of water that was displaced or that was pushed aside by his body as he entered the bathtub was equal to the volume of his body. So he made that discovery that any object will displace or will push aside water equal to its volume. So that means we can use these graduated cylinders to figure out what the volume of our objects are. Now the first thing we're going to do though is we're going to figure out what their mass is. So we're going to turn on our scale here, and luckily we're on planet Earth, so our gravity actually is going to be pretty much equal to our mass. So the first one we're going to use is we're going to figure out what the mass of our wood is, and if we look, that comes out to 3.2 grams. And I'll write that down here, 3.2, oops, let me write that a little nicer, 2 grams. Now, we'll figure out what our mass of our foam is. Our foam is only 0.5 grams, so just half a gram. So we're going to put down 0.5 grams. All right. Next, we're going to go to our rock. And our rock turns out to be 11.4 grams. And we'll write that down there. And then finally, our steel, we'll put that down, and that comes out to 20.4 grams. 0.4 grams. All right, so now we'll try to figure out what the volumes for these are. Now, first off, when I put these in, I bet you we've got a pretty good idea of which of these objects are going to float and which of these objects are going to sink. So, how about for our rock? What do we think? Yeah, it's probably going to sink. So, we're going to slide this down into our graduated cylinder. Now, we had set that level at exactly 70 milliliters. I just chose 70 because it was pretty easy to see 70 right there. Now, we're quite a bit above 70 now. Captain Jen, can you read that for me?
We are at about 74 and a half.
74 and a half. So the change from 70 to 74 and a half was 4.5 milliliters. So that was our rock. And so we're going to write down that its volume was 4.5 cubic centimeters. Oops. Right? Because we know that its volume is equal, its volume measured in cubic centimeters is equal to the volume of the water that it displaced, which was 4.5 milliliters. Let's take our rock, right? Excuse me, our steel. We'll drop that guy in. And Captain Jen, what do we got there?
So here we have about 73.
73. So our change was 3 milliliters. So the volume of our steel was 3 cubic centimeters. Excellent. 3. Now, we're going to try our two other objects. These, what do we think? These going to float or are these going to sink? Kind of betting they might float. So we're going to drop this in. Now, you notice that some of the wood actually isn't underwater. So to get a true measure of its volume, we're going to push it all the way under. Try to do this carefully. See if I can do it. All right. Captain Jen, can you help me out by reading that?
It's 75 and a half.
75 and a half. So that means the volume of this wood is 5.5 cubic centimeters, right? So we'll write that down before we forget it. 5.5 centimeters cubed. All right, and let's try the final thing, our piece of foam. And we'll try to get that in there too. And we'll push this down into the water. And Captain Jen, what'd you find?
73.
73. So that one displaced 3 milliliters of water. So it is 3 cubic centimeters. Excellent. All right. Now that we have those measurements, we can start to figure out the density, right? Because the density is equal to the mass of the object divided by the volume of the object. So our wood was 3.2, and we're going to divide that by its volume, 5.5. So that equals 0.5. Where did my, right. So that equals 0.58. And we're going to call those grams per cubic centimeter. Excellent. So let's do some quick math here, and we'll fill in, we'll do next our foam at 0.5 for the mass, divided by 3 for its volume, and we get 0.16666, which we can say is 0.17. All right. And our rock, which was 11.4, and we'll divide that by 4.5. That equals 2.53, which we'll round up to 2.5. Yeah, 2.53 we'll call it. Whoops. And then finally, our steel, which was 20.4 grams, and we're going to divide that by 3, and we're going to come up with 6.8. 0.8. So, obviously the things that sank are quite a bit more dense than the things that floated. Because we know that the wood floated, we know that the foam floated, but no and no. Now, I also left a line here for water. So maybe we can try to figure out what the density of water is. The way that we're going to do that is the first thing that we're going to do. We're going to take an empty cylinder. Let's weigh that. And that comes out to 8.8 grams. So 8.8 grams. And then we're going to measure one with 4 milliliters of water in it. Everybody see that that measures at 4 milliliters of water, and that comes out to be 12.6. So let's see, is it 12.6? Oh, 12.8, excuse me. So let's go here, 12.8 grams minus 8.8 grams, right? That was the weight of the empty cylinder. So that means the weight of our water is 4 grams. So we had a mass of 4 grams. We had a volume of 4 milliliters. So dividing 4 by 4, we get 1. 1 gram per cubic centimeter. So the density, when measured in metric, the density of water is 1 gram per cubic centimeter. So our floating objects, are they more or less dense? That's right, less dense. They're going to be less than 1. And our sinking objects, their density is going to be greater than 1 gram per cubic centimeter. So anything that floats is going to have a density less than water, and anything that sinks is going to have a density that's greater than water. Now, Archimedes, who figured out how to measure the volumes of these irregularly shaped objects, also did a little bit more figuring. He realized that there was a real big relationship between the amount of water that an object displaces or pushes aside and whether or not it can float. Now, if we had our rock, it sank right down to the bottom, right? But our wood, it floated. So if we looked back and we said our rock was pushing out of the way 4.5 milliliters of water, well, that 4.5 milliliters of water weighs 4.5 grams. Is that more or less than what the rock weighed? It's less, right? So, because it pushes aside less water, that rock actually sinks. Now, the wood pushes aside a lot more water than it actually weighs, so that makes it float. Archimedes figured out that for any object that's immersed in a fluid, so that's in a fluid, is going to have an apparent weight loss that is equal to the volume of the fluid that it is displacing. So if you think of an object, it has gravity pushing down on it. But if we place that object in water, some water is going to get pushed aside. Now, water and other fluids don't like to get compressed. So there is a force generated on the object that is pushing in on it by the water that it has displaced. Now, it pushes in on the sides, but it can't really do much there because the two sides cancel out. But it can push up. So the amount of volume of water, so the weight of that, is actually pushing up against gravity on that object. Pretty cool, right? So we can find that. Sort of helps us figure out why a boat can float.
Captain Eric, we have a question
Sure.
from Letty. And Letty would like to know, what about ocean water? Is the density the same?
Yes, that is a great question. Now, a lot of things can change the density of water. How much salt it has in it has a huge effect on how dense the water is. How warm or cold the water is has a big effect. As a matter of fact, ships have special rules for how much cargo they can carry in fresh water, in warm water, and in salt water. So all of that stuff does need to be figured out. But we're going to kind of simplify things, and we're just using fresh water today. Now, I have a ball of clay. Can we all guess what this is going to do when I drop it into the water? Everybody think it's going to sink? I do too. But let's measure its mass first. We come up with 60 grams. So 60 grams, we're going to put this down for 60. Excellent. All right, now what do we think? It's going to float or is it going to sink? I'm betting it's going to sink. So let's roll this into our big graduated cylinder here. And that difference should be 35 milliliters. So its volume was 35 milliliters, or 35 cubic centimeters, right? We can already see that the weight of water that was pushed aside by it was only 35 grams, which is a lot less than the 60 grams. So obviously our object is going to sink. However, I have another piece of clay here. This one I've fashioned into a really crude looking boat, right? Now, it's the exact same material as our ball of clay was. And guess what? When we measure it, it's going to be pretty much exactly 60 grams as well. So we have our clay boat. We're going to call it 60 grams. Excellent. Now what's going to happen, do you think, when we put this into the water? Let's find out. Well, there we go. Look at that, it floats. Something must be going on here. So I want to figure out maybe what the volume of this is, but unfortunately, it won't really fit into my graduated cylinder. And even if I did, I actually wouldn't be getting a measure of the full volume of this object, because we have to take into account the entire object, not just the clay, but the entire area that the clay surrounds. So luckily, we can actually measure this since I made it kind of rectangular. And it turns out that our little boat here is about 14.5 centimeters long. It's about 8 centimeters wide, and it's about 1 centimeter tall. So if we do the math there, we come up with 116 cubic centimeters as its area, right? Its length times its width times its height. that's 116 cubic centimeters, weighs, if I was to put this in the water and displace all the water with all 116 cubic centimeters, that's a lot less, or a lot more water that it's displacing than the 60 grams that it weighs. As a matter of fact, it's got room left over for more weight, right? So if we think this has 116 right here, that means we have at least 56 grams that we can add to this boat before it will sink. Do you want to try?
Yeah, let's try it.
All right. So we've got some pretty cool weights here. And these are great because you probably have a lot of these at home. We figured out that nickels weigh about 5 grams a piece, and pennies weigh about 2.5 grams a piece, so about half as much. So the first thing that we're going to do is we're going to put in some nickels. Doesn't seem to be having any problems floating those. So now the mass, 4 nickels, so 4 times 5, that's 20. So the mass of our object now is 80 grams, but it's still floating. So let's add some more. All right, so we'll put in 1, 2, oops. Hold on. Technical difficulties. Bad loading. Blame the longshoreman. All right, we'll try this again. Well, that one sank. Luckily, my boat is a little bit more sturdy than this. So 1, 2, 3. So that's another 10 grams. Now we're up to 90 extra grams. 1, 2, 3, 4. So now our weight of our object is 100 grams. 105 grams. 110 grams. You can see that it's not floating by very much. If I was in this boat in the middle of Narragansett Bay, I'd be pretty worried right now because just a little bit of wave action and the waves are going to start coming over the side of that boat. So I don't think that's a really good thing. Plus, I think my boat might have a couple of leaks. Let's try another 5 grams. We're now up to 115 grams. And let's see if we can keep going. 117 and a half. 100 and, let's see, that's 120 grams. So we're doing really well. Oh, what do you think? That's 125 grams. I think that if you remember back to our science of seawater demonstration, we might be getting a help by that because it looks to me like the water is already over the side of the boat. But if you remember Captain Megan telling us about surface tension, I think that's given us a help here.
Captain Eric, I think you just designed a great boat here.
I don't think I'd want to take it across the ocean. What do you think? Oh,
there it goes.
And there it goes. But we can see that by manipulating the shape of the boat so that it displaces a much larger volume of water than the boat actually weighs, that you're going to be able to not only float the boat, but you're going to be able to float a lot of cargo or people on board that boat. So that's why ships float and other objects float. I hope you guys have enjoyed our little demonstration here. If you'd like to try some of this at home, you can get yourself maybe some clay like I used, or maybe some aluminum foil, and try to fashion yourself a boat and see how much it can hold. Remember, pennies weigh 2.5 grams and nickels weigh 5 grams. And you can figure out how to design a boat that floats the most amount of pennies or nickels. Sounds like fun. Remember, clean up after you finish. And I hope you all have enjoyed our demonstration here and have enjoyed our breakfast by the bay. And if you're able, we'd love to have you donate to Save the Bay. But tune in again on Monday for another episode. And we hope you all have a great weekend.